as you reflux this and hydrolyze the ester, you form this dianion, which is water soluble. So what you'll see as the reflux occurs is slowly all of that white solid will disappear and you'll end up with a clear solution, and that's a good indication of when the reaction is actually done. Okay? At the end of the reaction, what you're going to need to do is let it cool, and then you are going to start acidifying the solution, right? Because in order to isolate your product, you can't isolate it as a dianion, right? We've got to protonate this back to get back a neutral small molecule. And so you'll see this as well. As you start acidifying, you convert this dianion into a neutral small molecule, which is not terribly water soluble. So as you begin acidifying, this will start to precipitate out again. Okay? So it's kind of cool. You start with precipitate, it disappears, and then you end up with precipitate again. Right? And in the end, you will just vacuum filter and get the crude salicylic acid product. Okay? After you get the crude salicylic acid product, you will need to purify that through recrystallization. I know recrystallizations are not the most fun things in the world. They can be quite tedious. Oftentimes, you have trouble getting your stuff out of solution. It can be a real pain. This is a different kind of recrystallization. It is a really easy one, dare I say, a fun one, because the product that you get from this are these beautiful, long, needle-like crystals. You'll probably want to post it to your gram. It's just that amazing to watch. But in any case, once the crystals have largely formed, you'll ice it and then vacuum filter those. Okay. So it's a pretty straightforward reaction. The only thing that I wanted to mention is, I think your lab manual says to use 1 molar sulfuric acid. We're not going to do that because it just requires so much of it. So I think I'm going to try to see if I can find some 6 molar sulfuric acid. Now, because we're using acid that's 6 times as strong as what the lab manual calls for, you're going to need to adjust the volume of acid that you use. Right? You're not going to use 75 mils or whatever it tells you of the 1 molar because you're using something 6 times as concentrated. So adjust that volume accordingly. The other thing it says, I think, is to check with litmus paper. Don't use litmus paper. I've got some universal pH paper that will be a lot better for that. You want to make sure that your pH is somewhere between the 2 and 3 range. You just want it to be fairly acidic. That way you can verify that everything on your molecule is protated. Okay. The last thing I wanted to tell you about was with the sodium hydroxide. So for those of you who have never worked with sodium hydroxide, sodium hydroxide are these little pellets. You need to make sure you do not touch the sodium hydroxide. It will burn you badly, okay? So do not touch the sodium hydroxide. As you're weighing it out, because they're little pellets, they can roll around a little bit. So it's really important. I know you come here and you look at the balances, and half the time they're covered with garbage from some careless, shall we say, student that came before, and whatever, you're used to seeing covered with chemicals. You cannot leave the sodium hydroxide on the balance, okay? Or anywhere else for that matter. If it happens to roll off the balance, you look at it and say, it's chemicals on the bench, I see it all the time. Don't do that, okay? Because they have a unique property of being quite hygroscopic, meaning they absorb moisture from the air. So if you leave a pellet of sodium hydroxide on the bench, after a couple minutes, it's not going to look like a pellet anymore. It's going to look like a little drop of water. And then some poor unsuspecting soul is going to come around and put their lab manual or their iPad, or worse yet, their hand in that little drop of water, and they're going to get seriously burned by it, okay? So if you happen to have a pellet go rogue, make sure you clean it up and put it in the chemical waste so that it doesn't harm anyone else, okay? The other thing is, because they are so hygroscopic, when you weigh it out on a weigh paper or your, what do you call it?
Watch glass.
The watch, thank you, the watch glass. You're gonna dump it into your water. If, the time it takes for you to get here to the bench, it may have absorbed enough water to where it's sticking to the watch glass or the weigh paper. If you go to dump it in and you have some that are kind of stuck, resist the urge to just tap it with your finger, okay? Again, you don't want to touch the sodium hydroxide in any way. If you happen to have some that are sticking, just grab a spatula and knock it in, okay? Do not touch the sodium hydroxide, it will burn. And then the last thing is the ester, the methyl salicylate that you're going to use. I have it here in a burette, in this burette right here. Please make sure you're paying attention to which burette you're using, because the 420 people are doing their Grignard reaction, and so there's stuff in these burettes. You're using this burette. Okay, they're all labeled. You just have to read which one you're getting. Okay, but you want to make sure that you are paying attention to the volumes. So think back to your burette use in Gen Chem. You always want to make sure you're getting an initial and a final burette reading so that you know exactly what volume of methyl salicylate you have got. Okay. Any questions about that? Okay, that's pretty much it. It's a pretty straightforward lab day. You're just going to reflux your stuff and then do the recrystallization. All right. We can go ahead and get started.